A separately derived system, or SDS, is an electrical power system that derives its power from a source other than a service. The key characteristic of a separately derived system is that it has no direct electrical connection to the service conductors. In the scenario described, the two 10 kV to 380 volts transformers within the plant substation create separately derived systems. The utility provides a 10 kV 3-wire feeder to the plant. This feeder constitutes the service conductors up to the point of connection to the primary side of the transformers. The secondary side of each transformer, providing the 380 volts output, then becomes a separately derived system. Understanding this distinction is crucial because the National Electrical Code, or NEC, has specific requirements for grounding and bonding separately derived systems, which differ from those for service equipment. The NEC defines a separately derived system in Article 100 as a premises wiring system whose power is derived from a source of electric energy or equipment other than a service. It has no direct electrical connection, including a solidly grounded circuit conductor to supply conductors originating in another system. For a transformer to qualify as a separately derived system, the secondary winding's neutral point, if one exists, must be isolated from the primary winding's neutral and the grounding system of the source. This isolation ensures that ground fault currents on the secondary side are managed independently from the primary side. Grounding and bonding are critical aspects of electrical safety and are addressed extensively in Article 250 of the NEC. For a separately derived system, Section 250.30 outlines the requirements for grounding. This section mandates that a grounding electrode system be established at the location of the SDS. The grounding electrode system can consist of various elements, including a metal water pipe, a metal frame of the building or structure, a concrete encased electrode, or a ground ring. The specific requirements for the grounding electrode depend on the size and type of the system. A grounding electrode conductor must connect the separately derived system's neutral point, if one exists, to the grounding electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the unbranded conductors of the derived system. Bonding is equally important to ensure a low impedance path for fault current return. A bonding jumper must connect the equipment grounding conductors of the separately derived system to the system's grounded conductor, if one exists, at the source of the SDS. This bonding jumper ensures that any fault current will quickly trip the overcurrent protective device, minimizing the risk of electrical shock or fire. The size of the bonding jumper is determined by NEC Table 250.102, based on the size of the derived phase conductors. The location of the grounding electrode connection is crucial. According to 250.30 AON, the grounding electrode connection must be made at the same point as the bonding jumper connection. This single-point grounding minimizes circulating currents and voltage differences between the grounded conductor and the equipment grounding conductors. Overcurrent protection for separately derived systems is another important consideration. The NEC requires that overcurrent protective devices be provided to protect the conductors and equipment of the SDS from overloads and short circuits. The size and type of overcurrent protective devices must be selected according to the ampacity of the conductors being protected and the characteristics of the equipment being served. Transformer protection is typically provided by fuses or circuit breakers on both the primary and secondary sides of the transformer. The primary side protection is sized to protect the transformer itself from overloads and faults, while the secondary side protection protects the downstream conductors and equipment. Coordination of overcurrent protective devices is essential to ensure that a fault on the secondary side will be cleared by the secondary side protective device before the primary side protective device operates. This coordination minimizes the impact of a fault on the overall electrical system. The NEC also addresses the installation of ground fault protection for separately derived systems. Ground fault protection is required for certain types of SDS, such as those serving sensitive electronic equipment. The purpose of ground fault protection is to detect and interrupt low-level ground faults that may not be detected by conventional overcurrent protective devices. Ground fault protection is typically provided by a ground fault circuit interrupter, or GFCI, or a ground fault relay. The requirements for ground fault protection are outlined in NEC Section 230.95 for services and Section 215.10 for feeders. While these sections do not directly apply to separately derived systems, the principles and requirements are similar and can be used as a guideline for designing ground fault protection for SDS. Another critical aspect of separately derived systems is the proper identification and labeling of equipment. The NEC requires that all equipment associated with the SDS be clearly labeled to indicate that it is part of a separately derived system. This labeling helps to prevent confusion and ensures that personnel working on the electrical system are aware of the unique characteristics of the SDS. The labeling should include the voltage, phase, and frequency of the derived system, as well as the location of the grounding electrode connection. In addition to the general requirements for grounding, bonding, and overcurrent protection, the NEC also contains specific requirements for different types of separately derived systems. For example, Section 450.3 addresses the protection of transformers, including those used in separately derived systems. This section provides detailed requirements for overcurrent protection, ventilation, and location of transformers. Similarly, Article 705 addresses interconnected electric power production sources such as solar photovoltaic systems and wind turbines. If a separately derived system is used to supply power from an interconnected power production source, the requirements of Article 705 must be followed. In the context of the described plant's electrical system, the 10 kV to 380 volts transformers create separately derived systems. Therefore, the NEC requirements for grounding, bonding, overcurrent protection, and labeling of SDS must be strictly followed. The grounding electrode system must be properly installed and connected to the neutral point of the transformer secondary. The bonding jumper must be sized and installed correctly to provide a low impedance path for fault current return. Overcurrent protective devices must be selected and coordinated to protect the conductors and equipment of the SDS. And all equipment associated with the SDS must be clearly labeled to indicate that it is part of a separately derived system. It's also important to consider the impact of the separately derived systems on the overall electrical system of the plant. The addition of SDS can affect the voltage drop, short-circuit current, and harmonic distortion of the system. A thorough analysis of the electrical system should be performed to ensure that the SDS are properly integrated and do not create any adverse effects. In summary, the 10 kV to 380 volts transformers in the plant substation create separately derived systems. The NEC requirements for grounding, bonding, overcurrent protection, and labeling of SDS must be followed to ensure the safety and reliability of the electrical system. A thorough understanding of the NEC and a careful design approach are essential for the successful implementation of separately derived systems. The separately derived system necessitates its own grounding electrode system, distinct from the main service grounding. This ensures that ground faults on the secondary side of the transformer are isolated and managed independently, preventing cascading failures or unwanted interactions with the utility's grounding system. The specific grounding electrode system can vary depending on site conditions and the presence of suitable electrodes, like building steel or buried water pipes. Proper bonding ensures a low impedance path for fault currents, facilitating quick operation of overcurrent protection devices. This includes bonding the transformer's neutral point to the grounding electrode system and bonding all metallic enclosures and equipment grounding conductors. The overcurrent protection on both the primary and secondary sides of the transformer is crucial. The primary side protection safeguards the transformer itself from overloads and internal faults, while the secondary side protection protects downstream circuits and equipment. Coordination between these protective devices is essential to ensure selective tripping, minimizing downtime and preventing unnecessary outages. Properly labeling the separately derived system components, including the transformer, panel boards, and associated equipment, is vital for safety and maintenance. This labeling should clearly identify the system as a separately derived system and provide relevant information like voltage, phase, and available fault current. Furthermore, it is paramount to conduct regular inspections and maintenance of the separately derived system to ensure its continued reliability and compliance with applicable codes and standards. This includes checking grounding connections, verifying bonding integrity, testing overcurrent protection devices, and inspecting for any signs of damage or deterioration. Ignoring this can cause an unsafe environment. The NEC Section 250.20b details circumstances requiring systems to be grounded. For alternating current systems, these usually involve systems with a voltage to ground does not exceed 150 volts, systems where the neutral point is grounded, or separately derived systems supplying only equipment. Section 250.30 provides rules for grounding separately derived alternating current systems. It mandates connecting the grounding electrode to the derived neutral point. The grounding electrode conductor size is based on the derived phase conductors, as specified in Table 250.66. The grounding electrode itself must comply with Section 250.52, including options like metal water pipes, building steel, or ground rings. Section 250.104d covers bonding requirements for separately derived systems. It dictates bonding the derived neutral to the equipment grounding conductors within the system. The size of this bonding jumper is determined by Table 250.102, also based on the derived phase conductors. The location of the grounding electrode connection and bonding jumper is critical. Section 250.30a requires both connections to be made at the same point on the separately derived system, minimizing circulating currents and voltage differences. Section 450.3 provides protection requirements for transformers, including those in separately derived systems. This includes primary and secondary overcurrent protection sized according to the transformer's rated current and impedance. Coordination of overcurrent devices is crucial to ensure selective tripping and minimize disruptions. Section 705.16 details requirements for overcurrent protection in interconnected power production sources, which may involve separately derived systems. These requirements focus on protecting the system from faults originating from either the utility or the interconnected source. Section 110.16 mandates marking requirements for electrical equipment, including separately derived systems. This marking must identify the system's voltage, current, and other relevant characteristics. Accurate labeling helps prevent confusion and ensures proper maintenance and troubleshooting. Section 310.16 provides ampacity ratings for conductors, which are essential for selecting the correct conductor sizes for separately derived systems. The ampacity must be sufficient to carry the load current without exceeding the conductor's temperature rating.